Hello, good morning, everyone, or good afternoon to some people, I guess. Depends on where you're from. Yeah, welcome to this webinar. So, first, big thanks to the people behind this event. So, thank you to Amelia, Anna, and Richard. They work for TUFCert and they have put in tremendous effort to make this webinar happen. Yeah, let me just check because I can not see how many. Oh, yeah, I can see people coming in. Yeah, so yeah, we can. I know there are more than perhaps 200 people registered for this webinar. And I can still see people joining in as we speak. So perhaps we'll give 1 or 2 minutes, just wait for more people to joining in. And in the meantime, I will just check with my colleagues here to see if everything works okay. Yeah. Okay, good. They said they can hear me perfectly. Okay. Yeah. All right. Okay. So yeah. So this is a sort of 45 minutes plus 15 minutes Q&A short webinar. And before I sort of prepared the materials, I was thinking, what kind of subject would be most useful to you who actually attend this webinar. Then I thought, okay, grounding is an interesting one, right? So I started putting slides together. And it's worth mentioning that I did present a similar subject called Demystifying Grounding and Shielding just 3 weeks ago in Silverstone in the UK, right? It was for the Ross Shores Demystify EMC event. However, in that event, I found using 45 minutes to demystify grounding and shielding is really impossible, isn't it? Because you've only got 45 minutes. But the reception was really well received, right? And we got more than 100 people attending that physical event. So today, actually, it was based very similar on the presentation I did for Ross Shores Demystify EMC show. But in this case, I sort of got rid of the shielding bit, and I really wanted to focus only on grounding, okay? So here we go. And so this presentation is really aimed to sort of junior to senior level engineers, especially design engineers. So we hope that after this webinar, you really understand, grounding as a concept or a definition, let's call it, particularly when it comes to EMC. And also some of the techniques we learned in this webinar, hopefully it will be useful for you to troubleshoot or design your product, okay? So we're going to start from some basic stuff and then move into a little bit advanced techniques. So that's basically how we're going to do this webinar. And as you can see from your screen, hopefully, you will see two windows, right? One is with the presentation slides, and the other one is actually a setup, okay? So this is my demonstration today, and we're going to use this demonstration to really show you the sort of the black magic when it comes to EMC, okay? So that's the plan. So let's start, okay? Right. So as I mentioned, these are the discussion points we're going to cover, okay? So to kick off this presentation, let me ask you a question, okay? So I have a very, very simple PCB here, right? So showing in the slides. And this PCB is placed over what we call test ground plane. As you can see, this is the test ground plane. And there is a insulation support, which in this case is just a cardboard box, between the PCB and the ground, okay? And it is powered by 12 volts. So we got red wire is 12 volts and black wire is the 0 volts, or some people call it ground, okay? And it is connected to a pair of listens. So this setup, right, showing here, or showing on the slides as the system diagram, is a sort of typical simplified benchtop-based EMC conducting emission setup. People who work in the aerospace, avionics, defense, and automotive, they are quite familiar with this test setup. Whereas for people who work in sort of industrial and home appliance applications, the conductive emission setup is actually quite different with this one. However, the principle is the same, okay? So that's the background of this setup. So you can see that on this PCB, I got 12 volts in and 0 volts. And I just have a very simple switch, like a MOSFET, okay? And it's switching at a frequency, as a frequency, basically just chopping. And for people who have experience in EMC, you know that if you have a voltage comes in as the input voltage, you have a MOSFET, you start to chop, you will create electromagnetic noise, or EMI as we call it, right? So I have a question for you, okay? So in this case, there's a test ground plane, so which is this one, okay? And this PCB has 0 volts, which is connected to the black wire, as you can see, right? 0 volts on the PCB. But it also has a quite, a big metal plate here. And this metal plate is a heat sink, okay? It's a heat sink. And as you can see that currently, this MOSFET showing here is sort of mounted on this heat sink with, of course, some thermal paste in between, right? So my question for you this morning to start the webinar is, now you can see here, I have a grounding lead. So this grounding lead is currently, one end is bonded to the test ground plane, okay? And the other end, I now have the ability to either ground the heatsink here, right, just by doing this, or I ground to a 0 volts, okay? I ground to a 0 volts. So which one is better from the EMC point of view, okay? So this is the question I'm asking. And the next one, I think you will see a poll here. So if you could participate in this questionnaire, there's only one answer, right? Either you ground the 0 volts, or the test ground plane to the 0 volts, or you ground it to the heatsink. So yeah, if you could just click the answer, and so I can see, your answers here. Okay, so that's my question for you. We're going to review the answers soon, and also, talk in details about, the physics behind it. Okay, so next. So we have the answer now, right? So based on the answers from the participants, we have about 62% saying we should ground the PCB 0 volts. That would sort of improve the EMC performance. And we had actually 38% people believe that we should ground the heatsink. That's great. Okay, so we've got like 2-to-1 ratio here, right? So let's continue. Okay, so before we review the answer, so let's really get to the physics behind it, right? So when we talked about ground, what do we mean? Okay, so here shows you a very simple, right, system diagram. This is a for example, these days, if you go to Amazon and you wanted to buy a fast charger for your laptop or your phone, you often find, on the website, lots of chargers claim they can do fast charging, and sometimes they say it's using GaN device or GaN techniques, right? GaN, that's the hot buzzwords these days. What it means really is now they started using a new power electronics device called gallium nitride. In the past used to be MOSFET, right? MOSFET has been widely used for many, many years, but now obviously we have the new wide band gap switching devices as a new technology. So people start adopting it, and you see lots of GaN device in the market. So this simplified diagram really represents that, and it is a double insulated product, so you often don't have earth in such products, right? It's just a plastic housing, but it really insulates well, so you don't really need earthing wire. So you've got live and neutral coming into the circuit, right? Then you have a bridge rectifier, a DC link, and the capacitor showing here really is a electrolytic capacitor typically, right? And most of the time, the switching mode power supply would have a isolated power supply. And in this case, it is a flatback converter. So you have a GaN device, as I said, these days as a switch, and you have sometimes a GaN or silicon carbide diodes on the secondary side. And then you have, of course, output capacitors, things like that. So you have, in the EU, you have 230 volts, 50 hertz mains power coming in, and you often get like 12 volts or 5 volts output, right? So that's how the circuit works. Just some information for people who are not familiar with power electronics, okay? But if you look at this diagram, right, and you can already see that because of the fact that you are using a so-called isolated switching mode power supply, you now have two grounds already. You have the so-called HV ground and the LV ground. So in this case, as we highlight here, the HV is HV minus, and the secondary ground is 0 volts. So now you already got two grounds, okay? So that's two grounds in this circuit. Now, if you want to take this product for EMC testing, how do we test it then? Well, or before we send it for testing, as I said, if it's a doubly insulated product, you don't have a earthing wire. But in some products, like the one I worked for a charger unit in the United States, they actually use a metal chassis. So in that case, you have another ground, some people call it chassis ground, okay, represented in this case in here as a chassis ground. And if you have a metal chassis, you probably will have a earthing lead, and that earthing lead is actually connected to the chassis ground. So now, if you have a product like this, now you have four grounds, right? You've got earthing ground, chassis ground, HV ground, and low voltage ground. So yeah, four grounds already. To make it even more challenging, right? So you take this kind of product, as I said, for a EMC test, because this is like more like a commercial or industrial product. As I mentioned, the test setup actually is a little bit different with the setup here. So basically, of course you have the test ground plane, but in the test house you will have an 80 centimeter tall non-insulated support, okay? And then you connect the live, neutral, and if you have earth, of course, to a device called artificial mains network. And then the artificial mains network is connected to another power supply, and then you test this product. So now, in your product, you have four grounds, and when it comes to EMC testing, you'll have another ground, which is called test ground, okay, test ground. And you have a receiver or spectrum analyzer that is connected to this artificial mains network. And what the receiver does really is to measure the voltage across a 50 ohm resistor. And basically, if you have noisy current going through that 50 ohm resistor, you pick up noise. And this is how we test conducting emissions. So the question for us is, with this system set up, where is my quiet ground? Because, like, if you look at the slides, when I say quiet, I put a quotation mark on it, right? Because people love the idea of, oh, I have a quiet ground. So where, I have a noisy ground, I have a quiet ground. And if you ask me where to ground my PCB, I would like to ground it to a quiet ground. So my question for you is, in this setup, where is the quiet ground? If you only are interested in passing EMC, then I can safely tell you, right, your quiet ground is actually the test ground plane. Why do I say that? Because as I mentioned, eventually, you are measuring the noise as referred to this test ground plane. So any voltage that is developed against this test ground plane is your noise voltage. So you should always use the test ground plane as your sort of quiet ground. But I don't like the concept of calling it quiet ground. So the best terminology of calling this ground should be RF reference ground, right? So it's a radio frequency reference ground. So that's the proper terminology of calling this ground. Okay, so now we sort of find our quiet ground, but now you have the challenge because you know that, in fact, this earthing ground showing here will have about 1 meter long cable lead, right? Even it is an earth wire, even if it is a green and yellow wire, which you think is good for EMC, but that wire has a 1 meter or sometimes even longer length. And for people who are familiar with sort of RF and EMC, you know that when it comes to cable, the most important thing is the cable length that forms a loop. So in this case, we have a loop, right? The loop is like this. This is the loop. And you have a 1 meter long cable. So that is a huge inductance, meaning, right? Think about inductance, meaning that at a high frequency between this earthing point and this test ground plane, you have a large impedance or reactance, right? Because the impedance Z here equals to R, which is a resistance value, which most of the time when it comes to EMC or RF, we ignore this R because, you know, it doesn't really matter when it is compared with the J omega L term, right? J omega L, and that L is the inductance. So inductance is important. So the point really is, once you find your quiet ground, you suddenly realize, oh, this ground actually is not really quiet against this one. This chassis is also not really quiet against this one, and not to mention the HV minus and 0 volts. So that is why, you know, the voltage difference or the potential difference at high frequency between your circuits, PCB or products, to the test ground plane is the main cause of your EMC failure. If you can somehow minimize that voltage difference, then you have a very, very easy time passing EMC, okay? So that's the point I want to cross. So this is actually an interesting case study, interesting story, right? You know, in the past, when we were doing EMC tests for internal combustion engine, if you speak to the tier 1 supplier manufacturers who makes these what we call electric control units, ECUs, they tell you that, okay, you know, the OEM, you know, the big guys like JLR, Ford, and they give you a EMC specification, and that is called subsystem or component EMC specification. And if you read it, they always have very similar EMC setup, right? So which I show here. This is a typical component level EMC setup where you have a test ground plane, you have, again, artificial means network or LISN, and then you connect it to device to the LISN, and then you test it. But for internal combustion engine, okay, that test ground plane you're looking at here represents what? Represents the vehicle chassis, okay? Represents the vehicle chassis. Now, it is all good when you're doing the internal combustion engine sort of design and tests. Obviously, now we're moving to a more electric vehicle world, right? Lots of EVs are available in the market. So when EV first came into the market, now engineers, especially EMC test engineers, were facing a challenge because now we have components, something, for example, in this case, the so-called onboard charger, OBC. This is an interesting one because the onboard charger actually needs to be plugged into the socket in your house or a charging station. So in a sense, it looks more like a commercial product rather than an automotive product. And if you look at the, you know, when you install the onboard charger in the vehicle and then you drive the vehicle, park the vehicle, and then start charging it, you now you're not looking at a very different setup, which is showing here. So this is the vehicle level conducting emission test. So you notice that the difference, right? So the 3-phase artificial mains network is the same, The cable length is the same. Onboard charger is the same. The only difference in this case is, in this vehicle test, the test ground plane here represents what? It's not representing the vehicle chassis anymore, but rather representing the Earth, right? In the Earth system in a charging facility or in a house. And obviously, if you look at the onboard charger, it is not really earthed to this test ground plane anymore. It is grounded to the vehicle chassis, right? Pretty similar like here, right? In this case, the onboard charger is grounded to the vehicle chassis. But between the vehicle chassis and the test ground plane, now you have non-conducted components because of the wheels of the vehicle. So because of this difference, when it comes to the component EMC testing and the vehicle EMC testing, we've seen a very consistent issue, which is a onboard charger that could pass the component EMC test sometimes by a good margin. When we say by a good margin, we're saying like 3 to 6 dB margin. And exactly the same component, the moment you put it on a vehicle and then you do the same test, well, I can't say it's the same test, but it's the conducting emission test, on a vehicle level, you start to see failure, especially in the very lower frequency range, like hundreds of kilohertz. So yeah, this is simply because in the two different test setups, the test ground plane represents two different things, right? For the component test, it represents the vehicle chassis, whereas for the vehicle test, it represents the Earth. Okay. So what can we do about it? Well, this is an interesting sort of joint exercise. So when I was working on this big electric vehicle, and showing picture here, you can see this test engineer called Rajesh. He was working with me at the time, very good test engineers. We just wanted to prove the point, right? When we failed the conducting emission on a vehicle level, we grounded the vehicle chassis to the test ground plane, and guess what? We passed. So really, it just shows you the point that it's a different grounding points we're using, and that leads to pass or fail. So that's quite important, right? On the left side of the slides, yeah, people were reminding me of using the pointer. Yeah, so I'm just trying to get the pointer working. Okay. So yes, yeah, okay, yeah, it's quite okay, yeah. So this side, okay, it's interesting. Yeah. So yeah, you can see this photo here. What I was doing, right, is I had a homemade what I call resistive probe. And this probe, if you just make a contact between the probe tip and the chassis plate where the onboard charger is mounted, then you can actually measure the surface current on this metal chassis. And in this case, when the onboard charger is being sort of in operational modes, we can actually see large amount of surface current. These are the noisy current on the surface on the chassis, and it can be picked up by either a spectral analyzer or a oscilloscope. So that's one of the techniques I often use. Okay, so it's indicating there's noise on the chassis, on the vehicle, but it cannot go to the test ground plane easily simply because the vehicle is not earthed or grounded. Okay, so that's a very large, sort of system, a big electric vehicle. Now, moving to a PCB level discussion. So this, if you look at the photo I took here, this actually is the unit I mentioned. So it's a charger and has a metal chassis, and it's a single phase powered, by the way. It's just charging some 12 volts battery, I believe. And it has live, neutral, and earth wire. And earth wire is connected electrically to the metal chassis. And of course, the PCB does the power conversion from AC to DC, and that's it, right? So I show you 3 grounding mounting holes on this PCB, okay? So first we have the earthing ground, which is here, okay? And then we have the HV ground, or we'll call it, where the HV minus can be connected to this ground point. However, you know that from the safety point of view, you cannot connect an HV minus to this mounting point. So in reality, you connect via a capacitor, a safety-related capacitor to this ground. okay? But we still call it HV ground because that's where your HV minus is connected to via capacitors. And of course, we have LV ground. So this is sort of like electric safe ground where you can just connect the secondary of your power supply, low voltage power supply ground to the chassis. So in terms of the mounting hole, we have 3 mounting holes. They can all sort of be connected to the chassis. And what I did at the time, right, was I used a current probe. Okay, so here in the screen, I show you this is what we call RF current monitor probe. So it's very useful for EMC testing, but most useful for EMC troubleshooting. I'm a big sort of, you can call me advertiser for RF current probes because I use it all the time. It just makes my life a lot easier. So what happened is I connect this RF current probe on both on live, neutral, and earth wires of this product, right? So what I was measuring at the time was the common mode current, okay, common mode current. And I did a very interesting experiment. So basically, because I have 3 mounting holes, so in theory, I have 6 combinations, right? I could leave all 3 holes not connected to chassis, or I connect 1 mounting hole at each time, or I could have 2-2 combination, or 3 mounting holes all ground or connected to the chassis. So I actually did some very interesting sort of experiments, and I compare from the noise point of view. If I measure the common mode current on the cable, I know how how this configuration would affect the common mode current. And so I presented this study here. It is quite interesting, right? Because if I just show you this result, we have green trace, and that is where all 3 grounds are connected to the chassis. And we also have the black trace, which is no grounds at all. So basically, all these grounds are not, none of these is connected to the chassis. So if you look at the frequency range from 150K to about 20 to 30, 20 megahertz for this frequency range, clearly the 3 grounding points has the best performance, right? Because the noise level is very low compared with all these other configurations. Without grounding is the worst, okay? So that tells you something. But another interesting part is if you look at the very high frequency here, sometimes when you ground 3 grounding points, it actually makes things worse. For example, this bit, right? So from, let's say, 20 megahertz to about 50 megahertz or 60 megahertz, you see the green trace where we have 3 grounding points, right? Actually has 10 dB sort of, it's 10 dB worse compared with no grounds at all, okay? Compared with no ground at all. But then you have, 2 grounds or 1 grounds, then you have different results. The point I wanted to make based on these results, right, is really like, the first point I wanted to make is every time you add 1 more grounding point, what change have you made? Think about this. What change have you made? You change how that RF current flow, right? Remember the previous slides where I showed you I have a surface current probe, resistive one, pointing on the chassis of the vehicle, and I can actually measure this surface current. That current will flow based on the impedance of the system. When you add or reduce grounding points, you are changing that path for the surface current. So they will flow whenever there is a low impedance path, right? So that is why the results will be different every time. Another lesson drawn from this is it is always better, right? Even though in this case you can see that over a certain frequency range, the 3 grounding configuration actually is performing worse. But if you ask me, I will still use the 3 grounding configuration because for a very wide frequency range, it's still the best, right? And yeah, here it is worse than some other configurations, but I can, add some future components and suppress the noise. So yeah, that's the 2 lessons drawn from this interesting case study. Okay, that's that one. So yeah, here I give you some real-life examples, right? So this is a DC-DC converter for an automotive project. The PCB layout engineer, he's a very, very good, very experienced guy. And in this case, this is a buck boost converter, but he was telling me that he followed the manufacturer's sort of guideline of creating a split ground, which caused problems actually, right? And then in order to prove that the split ground is not a good idea, here you can see what I did at the time, right? So this is their sort of noisy ground, if you call it, and this is their sort of the quiet ground. And at the time, they actually split ground. So what I did, the first step was to scrape the paint and then put solder on. And rather than sort of shorten these two grounds as a first step, I often start with capacitors. Why? Because capacitors, you know that in the sort of low frequency range, DC to a few tens of kilohertz, they are high impedance. And when it comes to RF, high frequency range, they become short circuits. So if you really wanted to prove the concept, right, or prove a point, I start with capacitors. So I mounted the capacitors between two grounds and I perform the same test. As you can see that when I use one cap, just joins the two grounds, you can see a significant improvement in the lower frequency range. So here, in terms of the noise, we are talking about more than 30 dB improvement in the lower frequency range. So that demonstrates the point. Okay, and following that, so the next photo down here, right here, yeah, I'm still trying to get used to this pointer thing. You can still see that's the sort of the separate grounds, which we already, at the time, we already bridged it using copper tape and solder. But there's another two grounds, which I think they should be electric connected. So that's what I did at the time. I used a short wire connection. And again, you can see improvement in the results, showing green against the yellow, right? And then, you know, because I mentioned, right, even this short wire here, as you can see, is probably just 1 or 2 centimeters long. That has actually 10 to 20 nanohenry inductance. So from the very high frequency point of view, it's still not efficient. For low frequency, no problem, right? Because low frequency, your impedance is still low, but for high frequency, this inductor actually becomes a high impedance path. So as you can see from this photo here, I improved the grounding by putting copper tape, because copper tape, I can create an area which is large, so low impedance for RF, and I solder it in this way. And then you can see now, even in the high frequency range showing here, if you look at the green trace against the magenta, you can see a big improvement here, okay? So yeah, avoid splitting grounds when possible is the lesson on this slide. Even though the application notes might tell you otherwise. Okay. So far we discussed the vehicle level. We discussed sort of component level, you call it. Now let's have a look at another case study, which is in a rather large system. Okay. So you can see this is a very big unit. I'm sure today we're sitting here, many people actually work in a big sort of large system, large unit. So hopefully the lesson drawn here is also useful for you. So you can see in terms of the EMC test setup, we have a 3-phase LISM, and we have isolation transformer, and we set up a test ground plane. Because if you want to sort of repeat or create a benchtop test setup, always make sure that the first thing you do is making sure you get that test ground plane, right? Showing we know that test ground plane is important as we showed you earlier on. Okay. Anyway, so this is the conducting emission results we got. Clearly, it failed, right? And it failed at 2 frequency points, okay? So the first one is sort of 400 and 500 kilohertz, and the next one is about 2 megahertz range, and they all failed the conducting emission. So when we were troubleshooting this unit, I already knew how to solve this problem, this hundreds of kilohertz issue, is because they have a filter and they only chose the 3-phase 3-wire filter, whereas they should have gone for the 3-phase 4-wire filter. So once we started once we use the 3-phase 4-wire filter, this noise can be brought down. However, we were still struggling with this noise here, megahertz noise, okay? So, right. Okay, so we see just a quick answer to the question. Somebody asked, do we use a swept-based spectrum analyzer or real-time? So in all these case studies here, I was actually using sweep type or swept type spectrum analyzer. And if it's just troubleshooting sort of conducting emission noise, there's no need to go for the very expensive real-time one. Although the real-time one does bring you benefit. Okay, we can answer all the questions later. I just saw this question. Okay, and yeah. Anyway, so in order to troubleshoot this issue at 2 megahertz, right? What we did at the time was, you can see here is the Andrew, the supporting engineer. He was using a special device I had that can that can measure the ground bounce, what we call ground bounce, or it's just ground difference, very accurately, especially in the RF range. So in this case, he was measuring 2 grounds. The first grounding point here is where the motor drive was mounted. So the motor drive was mounted on a big sort of steel plate. And then here, this end, is where the filters were mounted. And they are connected electrically, right? If you're using a sort of ohm meter, you probably will be surprised. Oh, yes, a low resistance measurement, right? Low resistance, maybe 20 milliohms or something like that. You think, oh, and they're electrically connected, but not for RF, right? As I mentioned, RF is the reactance of inductance rather than the resistance. So by using this method, where we're basically measuring the voltage difference between the 2 grounding points, and we did actually both the time domain analysis and the frequency domain analysis. So both showing here. So in the time domain analysis, we have measured 15 volts peak to peak, as you can see here. That's the noise voltage between the 2 grounds. And in the frequency domain analysis, you can also see, first, remember this one, this is the hundreds of kilohertz noise. We can see that, but we can also see that 2 or 3 megahertz noise. So that's good. That means, okay, if we can sort of, remember I said, when you have 2 grounds, if you can somehow minimize the ground voltage difference, then your job is a lot easier for passing EMC, okay? So what did we do? We actually use many more wire connections now, as you can see here, between the 2 grounds. So this is a sort of braided wires, right? And we sort of ground the 2 points. And you can see the improvement. One point I would like to point out is that actually in this case, the frequency domain analysis, you can't really see the improvement here, right? You may be able to see about 3 to 4 dB here. So it's not that obvious. But the time domain is much easier, because now you can see it's half of the voltage, from 15 volts to 8 volts. Why? Well, if you're familiar with the dB term, if you look at 3 dB or 6 dB, it's just double. It depends on whether you're using voltage or power. But so 3 or 6 dB often is not easy to spot. So then you move to the time domain, you can really see the half. How in this case the noise voltage is halved. So that's a good sign. We could even make things better. So this is the final application, as you can see. I was using this shielded cable, but I wanted to point out here, right, is that in this case, the shielded cable is inside the cabinet. So it actually does not do shielding as many people think, right? Why do we use a shielded cable here? Well, because when I use a shielded cable on the wires, I can then ensure both ends are grounded properly to both grounds. So in this case, the shield itself provides a low impedance path between the 2 grounding points I wanted to ground, right? So you can see here, even here, I tape it using a copper tape so that the shield is also sort of grounded to the same ground potential. Once we implemented this, we repeated the test, and then you can see here, the noise level is well under the limit line now, with at least 3 to 6 dB margin. So if you can see this in your factory when you are sort of doing the pre-compliance or benchtop EMC tests, then this is a good margin where you can probably confidently send this unit to accredited EMC test lab and do the test. Of course, in this result, we still have a failure here, but as I mentioned, that's due to the filter issue, which we later swapped the filter and the problem was solved. Okay, but the focus on this slide is really the noise here. You can really see the big difference. It's more than 10 dB brought down simply by making a better ground connection in a large system. Okay. All right. So yeah. So time is 42 past 10. We still got about 5 to 10 minutes. So I wanted to demonstrate the setup. Okay, and then we'll close the sort of the question, the presentation. Okay. So as you can see here, I have the setup already set it up. Okay. And the spectral analyzer in this case is connected to the LISN, so it's measuring the conducting emission noise coming from this PCB. Okay, so now I disconnect this grounding point first. So we first do a bench conducting emission scan on the PCB itself. Okay, so let me switch on the power supply. So power is switched on. And you can see there's a red LED light indicating the unit is working now. And you can also see noise start picking up from this spectral analyzer. I wish I could sort of zoom in this camera, but I don't want to mess with it. So hopefully you can see this. Okay, so this is the noise we measured just by the PCB itself. Okay, so if I save this trace, so let's go to trace 1, and I freeze it. Okay, so that's trace 1. Now I'm enabling another trace, which is trace 2, showing in magenta color. Okay, now let's have a look when we ground the 0 volts. So I'm going to connect this short ground lead between the test ground plane and the 0 volts. Okay, so this is what I got. So can you see that? So this yellow, as I said, is the bench result, and the magenta one is when we connect, when we sort of bridge the 0 volts and the test ground lead. So I'm just checking our audience feedback if they can see it properly. Or perhaps our team can feedback. Okay, yeah. Anyway, so this is let me also save this one. So we've got a reference here. Then I'm enabling another trace here, blue, where I connect the heat sink. Okay, so this is when I connect the heat sink. So it's in blue. Okay, so what I'm going to do is I'm trying to move the camera, so hopefully then you can see the screen better. If it's helping, how do I do that? Let me do that. Perhaps, yeah. So this is perhaps is better, right? So yeah, yellow is the PCB by itself, magenta grounding the 0 volts, and blue is grounding the heatsink. Okay. So yeah, congratulations to those people who got it right. Okay, back here again. Right. Okay. So so then the next question is why, isn't it? We need to answer that question. Why is this the case? So let's have a look. My slides. Yeah. So when we will look at it, right, is the so-called common mode current. Unfortunately, today we don't have enough time for those people who haven't heard about common mode current or always struggling to understand common mode current. So I'll just do a very quick demonstration here. Okay, so in the first case, where it's just the PCB by itself, right? Once the switch starts to switching, it has parasitic capacitance to the heatsink, okay? Because the heatsink has a large area, as we can see there, right? And between the heatsink and the test ground plane, also we have the so-called parasitic capacitance. So through these parasitic capacitance, the noise as a current form actually form a loop. And it is this current that is being picked up by the spectral analyzer, hence we see the noise, the conductive emission. Okay. Now, if we ground the 0 volts to the test ground plane, you are effectively, think about it, what we say, the 0 volts as a ground and the quiet ground as a test ground plane now, because we're using a very short connection, so the voltage difference between the 0 volts and the test ground plane is now rather small compared to the first case, okay? So that's what is happening. So this is a demonstration I show you here. So another way of seeing it is because now you ground the 0 volts to the test ground plane, okay? Here, you now provide a much shorter path for the noise current. Remember what I said on that slide where we use multiple mounting points, right? I said every time you add in one more grounding point, you effectively change how the RF current flows. And in this case, because we ground the 0 volts to the test ground plane, the RF current now see, oh, this is a much shorter path for me to flow. Why not, right? The nature also wants to save energy. So as a result, lots of the current, right, will circulating in this much smaller loop. So as a result, you get less and less current in the other loop, which is here. And when you have less current in the other loop, you have less noise, right? Simple. So that's why by grounding the 0 volts to the heatsink, it brings you benefit. Oh, sorry, by grounding the 0 volts to the test ground plane to bring you benefit. So why, okay, next is we ground the heatsink, okay? So in this case, the only difference is rather than grounding the 0 volts, now we connect that heatsink to the test ground plane. Now you see the current actually is increasing because the fact, remember, initially before you ground the heatsink to the test ground plane, you rely on that parasitic capacitance showing here, this green one. This parasitic capacitance is the only path for your noise current to flow. And this is, is a capacitor. So it has impedance in the lower frequency range, and it only goes to hundreds of megahertz. You start to see it's almost like a short circuit. But now you still have this parasitic capacitance for high frequency. At the same time, when you ground the heatsink to the test ground plane, you effectively provide a lower impedance path between the heatsink and the test ground plane. And remember, this heatsink is not your 0 volts, right? It is just a massive radiator. You can treat it as this, right? It's not a 0 volts. So as a result, rather than circulating the current is actually injected to the test ground plane. That's why you see an increased level of common mode current contributing to conductive emission. Another thing worth noting is that how do I, you can just say, yeah, man, that's how you interpreted it, right? That's how you explain it. But how do we know is actually this is what's really happening? Well, one test we can do is to put a current probe. Remember the current probe I showed you up here? And you can clamp it on this short wire. And then depends whether you connect to 0 volts and the heatsink, you can actually see the current level. Okay, so you can definitely see the current level in the time domain measurement, but also you can see the direction of the current. And that's important because in this case, as you can see, when the noise increases, the current actually is injected to the test ground plane. So it's going this direction. Whereas the previous case, if I show you back, when we ground the, so let's just go there. When we ground the 0 volts, if you look at the current, the arrow, okay, so you look at the arrow. The arrow actually is this because it's a circulating current rather than injecting current. So when you perform a time domain measurement using an RF current probe, you will be able to see that current reverse phenomenon doing that. So I actually did that, and I wanted to share with you how I measure it today, but I just realized, again, it's always the problem, we're running out of time. So we only got 10 minutes left. So unfortunately, we couldn't show you this in the time domain measurement, but I hope I explained in a simple way where you can actually understand. But if you want to see it, don't worry about it, because I have a YouTube channel. Just go to YouTube and search Minzang EMC, you probably will find me. And I hope to bring this into the YouTube channel perhaps in 2 weeks or 1 month's time. And yeah, so that's the end of the presentation for today. So let's just quickly sum it up for everyone, okay? Points to take away. I only give you 2 points to take away, right? The first point is the purpose of EMC grounding is to make interference voltage low compared to the desired signal or compared to your quiet ground, which in the EMC test scenario is your test ground plane, okay? And second point is the EMC ground is a low impedance path. Always remember, low impedance path for currents to return to their source, just as we show you in this case. If you can connect the 0 volts to the test ground plane, you are providing a low impedance path and return that noise back to its source. Okay, so that's the end of this presentation. So one more thing I want to mention, right? So since you stay here to the end, now you can have this discount code is webinar _10 for you if you want to sort of register yourself for one of the TÜV Cert Academy training course. You can use the code. It will give you 10% discount. And as I mentioned, yeah, it's just a shame that given the limited time, we could not do the final demonstration, but you're always welcome to check my YouTube channel. And yeah, and that's it. If you want to learn more about EMC, I would recommend, of course, the TÜV Cert Training Academy, which is always popular. You have to book in early. Otherwise, there are good EMC conferences you can attend. In the UK, there is EMC and Compliance International, which is scheduled for May. So if you want to attend, check that conference. So that's today's presentation, and I have 5 minutes for questions. So let me just quickly check my Q&A. Okay, so we have some comments and some questions. So this is a comment from Patty. Says also, yeah, Patty said, would connecting the heatsink to the grounded 0 volts be a solution? Yes, you're right. So in fact, when you are doing a design where you have the heatsink, it is always recommended to ground that heatsink. But the question is, ground where? So most of the time, from experience I had, always try to ground the heatsink to the 0 volts on the PCB. Of course, I understand this is sometimes tricky, especially that heatsink itself carries, so a good example is if the heatsink is connected via thermal paste to a high voltage switching devices, then in that case, you cannot really ground that heatsink to 0 volts, isn't it? So the solution, there are two. You either ground that heatsink via a safety class capacitor to that 0 volts. Alternatively, you can use a electrostatic shield in between the high voltage switching device, thermal paste, and the heatsink, and then you can ground that electrostatic shield to the 0 volts without any issue. So yeah, there are solutions to this, but yeah, typically speaking, for low voltage system, always a good idea to ground the heatsink to the 0 volts on the PCB. Also, one point to add is that how many grounding points you should apply between the heatsink and the 0 volts. Again, depends on frequency you're concerned. If it's a high frequency noise source, for example, if it's a microcontroller that switches sort of megahertz or hundreds of megahertz range, then you do need many grounding points, as many as you can. If it's just something like switching at tens of kilohertz, then 2 grounding points perhaps will just do the job. Okay, so that's one question from Patty. Hopefully this satisfies your question. Next one from Phil. What happens if you connect those? Yeah, so this is the same question almost. Adam says, what would have happened if you ground those? Oh yeah, same question again. In fact, I just wanted to mention this demo board has the capability of doing many demonstrations. Again, we can't cover it in today's session, but hopefully in next one, right? Because you can see here I have a switch, right? I can switch to another MOSFET, which has the heatsink grounded to 0 volts, and you can actually see the noise comes down. And then I switch to another MOSFET, which basically which has the heatsink, but the heatsink is floating, right? It demonstrates a few points. And today we're just demonstrating one point, but this board, the way I made it, that can be used for many demonstrations. Hopefully we'll show all these interesting findings with you in the sort of next seminar also, right? Right, so yeah, I guess at least our audience today all seems to have a very good understanding EMC, because you're actually asking really sort of good questions. So yeah, I hope this is okay with you. And yeah, I think that's all the questions I got. But yeah, so thank you for your attendance. It's much appreciated. We still have 100 people left. So yeah, big thanks to you. If you spot any sort of error or something you don't agree from today's presentation, feel free to drop me an email, and you probably can find it on the TurfCert website. I don't work for TurfCert, but I work with TurfCert, particularly on the EMC and RF side of things. So you should be able to find my contact details if you have further questions or comments on today's presentation. So yeah, other than that, I wish you all have a good rest of the day, and see you soon.